So laser beam machining is another non-traditional process. Again, when we mention non-traditional process, then it doesn't have physical cutting tools to remove materials. Okay? So introductions. Laser is an abbreviations for it's abbreviations for light amplifications by stimulated emissions of radiations. So the laser itself, stands for those, light amplification by stimulated emissions of radiations, and the name itself actually explain how this thing works, the theory behind it, where the light being produced through amplification. So the heat source that actually doing the cutting is actually from light amplifications. And this light amplification actually is produced uh, by stimulated emission of radiations, where the atoms of the laser materials is stimulated, uh, and it produce photon, and this photon is collected and being amplified. Then you have light amplifications, which is laser. So laser is highly collimated, meaning that it's directional. It's very directional and monochromatic. So compared to regular light, which consists of many different lights, but laser is monochromatic. So it has a specific light uh, um, for specific element. And coherent light beam is generated and focused to a small spot. So these three things, collimated, directional, monochromatics, and a coherent light, is the characteristics of the laser, and you can focus them into a small spot, and because of that, then you can get a very focused energy, which can burn, and melt and vaporize material. So when you talk about laser, you're talking about very high power density. You're talking about 10 to the power of 6 watts per millimeter squared. So this is a very high intensity, and you can have this laser in two form. One is continuous wave, which is designated by CW, or pulse mode of operation. So depending on type of laser, then you can have it in either continuous mode or pulse mode. So continuous mode means that basically if it's pulse mode, then what you have is if it's a pulse mode, then basically what you have is you have if you have this is power, this is time scale. So if it's continuous, then the power is continuous. If it's pulse mode, then basically what you have is, this is again power, this is time, then you have a pulse. So the power is in terms of pulse, just like when we talk about EDMs, on and so forth, where they have a pulse on and pulse off. Okay? Lasers are widely used for many industrial applications, including plating, heat treatment, so on and so forth. So basically, you can use laser not only for machining, but you can also use it for plating, heat treatment, cladding, alloying, welding, so on and so forth. And we're going to go through at the end of this particular chapter. Not only we're going to look into machining process using laser, but we're going to look into welding. Not sure whether heat treatment, welding, and some other applications of laser in processing of materials. Okay. Any questions? Right. Okay, fundamental of laser. So first, what we need to understand is we need to understand how the laser is generated. Laser is generated. So if you look at this particular schematic in here, so this is a laser tube. So in the laser tube, you have a lasing material, a lasing medium. So this can be gases, or it can be gases, it can be semiconductor material, so on and so forth. Right? So we call this material is a lasing medium. Right? And whenever when there is no power supply to the lasing material, then you're talking it at the ground state. Right? So this is a laser tube, and on one end you have high reflector, meaning that you have this particular section. This is like a mirror which reflected 100% of the light coming to it, right? On the other side is output a coupler, and this is we call it partial reflecting mirror. So some of the light will be reflected, and some of the light will go through this particular mirror. So you have two basically lens mirror. One is 100% reflecting mirror. The other one is partial reflecting mirror. And in center, basically what you have is you have a tube, and you have a lasing material inside the tube. So explanation for it is an electron can absorb energy from a variety of external source. So inside this tube, basically you have lasing material, as mentioned just now, gas, liquid, solid, so on and so forth. Right? So let's say, for example, this is CO2 laser. So in here you have CO2 atoms. Right? So if you look at atoms, you have atoms, and around the atoms you have an orbit. So if you have an atoms here, if you have an atoms, what you're going to have is you're going to have atoms, and you're going to have orbit around it. So this is where proton and neutron is at the center, and then over here you have electrons, right, in the orbit. So these electrons basically at its stable conditions, then these electrons exist at this stable and what do you call it, position, right? So this is what happened initially, right? So it says that electron can absorb energy at variety external cause. So when you pump energy, and usually the way to supply energy, the lasing material is through light, flashlight. So you have a flashlight here. It's not regular flashlight, but we call it flashlight, that actually supply energy to the atom. So when you supply energy to the atoms, basically you have this happen: electron absorb energy, and the increase of energy of the electron causes it to jump to a higher energy level. The atom is said to be in excited state. So basically, uh, going back to here, so you have electron here, right? So this is at the stable stage, right? This is at the uh, equilibrium stage. But when you supply energy to it, this electron from a lower orbit, it might jump into a higher orbit. So this guy might jump up here, right, to higher orbit, and this guy might jump up here to next higher orbit, right? So this happen if you supply energy to the atom. So electrons will jump from lower orbit to higher orbit. So let's say, for example, this is at energy band 1, this is energy band 2, this is energy band 3. So when the atoms got external energy, electrons will absorb that energy, and it actually will jump into a higher level. Uh, population, so this is said to be in the excited state. So these atoms will be in the excited state. When the population inversion happen, there's more. So when more and more atoms at the excited states means that the electron jump to a higher level of energy band. So if more atoms at high energy band has possessed electrons at high energy bands, basically then what you said is population inversion is achieved. So when population inversion achieved indicates that more atoms is at unstable state compared to its stable state. So any questions? Okay, and then what happened is an excited electrons at a higher energy level will soon attempt to de-excite itself. So like any unstable materials, right? Like unstable materials, it tries to go back to its stable conditions. So the jump in it, the electrons that jump to a higher band will try to go back to the lower band, to the stable conditions. So when this happens, so at this particular point, this electron is at E3, right? And E3 is greater than E2. So energy at band 3 at here is greater than energy at the lower band, which is E2. So when the electron jump down to E2, so if the electrons move from E of band 3 to E of band 2, basically then there's energy release. So basically you're going to have energy release in terms of photon, right? So so the excited electrons at a higher energy level will soon attempt to de-excite itself. So it tries to de-excite itself going back to a lower level. So the excitation cause spontaneous emission of photons. So because of that, because the jump from high energy level to low energy level band, then basically you have to release an energy. So in order to release energy, then the energy is being released in terms of photon. And this photon released from the excited atom clouds upon interacting with second similar excited atoms triggered the second atom to excite itself and release another photon stimulated emission. So a stimulated emission will happen when this photon releases its energy, when the electron releases its energy in terms of photon, right? And other excited atoms also do the same thing. Then basically they will do the same, they will release the same energy, photon, simultaneously. And this is called stimulated emission. And the energy that's being released, the photon that being released, is basically in the same wavelength, so on and so forth, in the stimulated emission photon. So they are all in sync in terms of wavelength, so on and so forth. So the photon will be reflected by the mirror on the end of the lacing rod or tube. So basically, once you release the energy, the light will move in many directions. But the one that's actually moving in the horizontal directions, going to this mirror or going to that mirror, will be reflected. Will be reflected. The ones that's moving not towards the mirror will lose itself in terms of heat, so on and so forth. But those that's moving in the horizontal direction will be reflected. Right? The reflected photon then pass back through the material triggering further emission. So the photon will go back and forth and trigger more emissions. Okay? And this amplification process continues. A portion of radiation will always escape through the partially reflecting mirror as a laser beam. So as this going on, basically some of it will pass through the reflector, because if you remember, this is the left hand side is high reflector, meaning that it reflected 100% of the light. But on the right hand side is a partial reflector. So at certain stage, then basically the light will be released and let go from that particular reflector. So Based on that, then basically then you have a laser beam. So the process in creating laser itself is basically that you must have a lasing material. You have two mirror at the end of the laser tube. One is high reflector, reflecting 100% of the beam. The other one is partial reflector, right? And then you supply, you pump energy. Usually this is using a flashlight. They call it a flashlight. And once the electron get excited, meaning that the electrons of that particular atoms jump to a higher level, and more than half of the populations of the gas achieve the excited stage, then you're talking about yeah, that you call it population inversion. So when that happens, then basically the tendency is for the electrons to go back to its stable state. So it will jump from the higher band to the lower band. That release photon in terms of energy. And when more and more photon release at the same time, we call it stimulated emission. And this photon, which is light, will be reflected back and forth through the mirror, right? And this will actually produce more emission. So at certain stage, then basically you have enough photons, then and some of it will be released through the refractor, uh, partial reflecting collector, and you produce a laser beam. So that's basically the basic fundamental of laser, how laser is being produced. Okay, any questions? Okay, so so looking at the component of the laser system itself, so laser system usually will have you have something like this. So this is a helium neon laser system. So you have a laser active medium material. So you have a lasing material itself, and this can be four types, which can be a solid state. It can be solid state like a ruby, so crystal like ruby. Can be solid state gas, uh, CO2. So the uh, the one that you use in UTEM to fabricate your project is actually CO2 gas. You can have lasing material of dye or semiconductor material. Right? So these are some of it materials that can be used as a lasing material. So basically, there must be an active medium contain atoms whose electrons may be excited to a metastable energy level by energy source. So you want to the lasing material must be active medium, uh, whose electron can be excited to metastable energy level. So metastable energy level is basically is a unstable state of the atoms. Uh, so uh, so it's metastable state. So let me just show you. So if this is so if you're talking about energy level, so this is so when the electrons jump, you release electrons, the energy of the uh, uh, so if the electrons atom receive an energy, electron jump to a larger orbit. So its energy level is at this E1, for example, right? So sometimes the electrons would go down. So this is stable. This is stable state. So this is excited state. This is meta state. So sometimes if you excite if you pump energy to the lasing materials, then the electrons jump up. But that particular atoms is stayed at the excited state. So this excited state. sometimes before it goes to the and it always wants to go to the stable state down here, but sometimes it'll move from there to here to the meta stable state first before it jumps down here. That's what they meant by this. Active medium contains atoms whose electrons may be excited to a meta stable energy level by energy source. Okay. Uh, so so that's one. Second, so you must have a lasing material. So lasing materials inside the laser tube. Second, you need to have excitations mechanism. So you need to have a means to supply energy to the lasing material. So one of which, so excitations mechanism pump energy to the active medium. So that if your medium is CO2, then it pump energy into CO2. If it's YAG laser, then it pump energy to ND-YAG materials. Okay. Uh, so excitation mechanism pump energy into the active medium by one or more three basic methods. So there are three methods of pumping the energy. One is optical, second one is electrical, third one is chemical. For example, in this particular YAG laser system, basically you have a flash lamp. So flash lamp is the pump source, which actually pump energy into YAG crystal, which is a lasing material, lasing medium. Third, you need to have so first you need to have the lasing material itself. Second, you need to have excitation mechanism. Example, flash lamp. Third, you need to have a high reflectance mirror. So one side will have high reflectance mirrors which will reflect essentially 100% of the laser light. And the fourth element, basically you need a partially transmissive mirror. So a mirror which reflects less than 100% of the laser light and transmit the remainder. So these are the four components that's crucial in laser system. Okay, so again, this is the schematic of it. So you have a reflecting mirror. Over here, you have the lasing laser tube. So lasing material is inside here. So you can excite it using some excitation power. In this example is a flashlight, right? So this is a partial reflecting mirror. So some of it will pass through. So this is reflecting 100% of the light of the laser. This will reflect partial of it. So this is the focusing mirror, and this CNC control position table which move the table, and from here to here is focal length. So if you look at the laser type, you can have mentioned just now. You can have solid. You can have semiconductor materials. You can have gas, and the other one you can have dye. So depending on different materials that you use, it will have different wavelength and different type of performance. For example, if you talk about YAG ruby, it can only produce pulse laser. It cannot use continuous laser. And this is basically the laser power, typical performance laser power that it can produce. So if you use ND-YAG laser, then you can do both pulse and continuous laser. And this is the power used. So the one that we use basically in our lab is CO2. So this is it can use pulse, it can produce pulse or continuous laser. This is basically the wavelength that's being produced with various materials. And this is very important because depending on the wavelength, then it can cut certain materials and cannot cut certain materials. We're going to go through that later. So this is a types of laser being used in industry. Some of we have a solid state laser. Solid state laser usually use ruby and the YAG laser. So YAG laser stands for neodymium, yttrium, aluminium, granite. So this is YAG laser. Or you can use a semiconductor. A semiconductor, sometimes they call it a diode laser. Yeah. So if you look at the solid state laser, if you look at YAG laser, this is basically the wavelength. This is the wavelength for the semiconductor laser. So this is in the applications of laser printer or CD. So if you use laser printer, there'll be a laser produced to actually burn the powdered materials. So you have imprint on your paper or to read your CD player. So usually those applications use semiconductor laser. So a gas laser, uh, uh, like helium neon or CO2, a gas laser. So these are examples of materials that's being used as lasing materials, or excimer laser. So excimer laser use reactive gas like chlorine, so on and so forth. And this is the wavelength that's being used. So in the individually, there's way to stimulate the lasing materials. For example, if you use this electrically stimulate, this is light. If you use helium neon or CO2, basically you're going to use a flash lamp to excite it, so on and so forth. Right? Or is fiber laser within the dope fiber. So this is, for example, this is your fiber cable. So this is your fiber cable. So if you use your internet system, use what do you call it? Use uh, not streaming. The other one is what? The one that fast. I forgot what is it. So then they use a fiber rather than copper system. So if it's fiber system, then the signal is carried through the fiber using laser medium. So let's look at the material removal mechanism quickly. Uh, Again, we have about 6 minutes. So if this ends, then basically please log in into the next session. Um, if you have any questions, please ask through either chat or unmute yourself and then speak up. Right? So the removed material mechanism is basically this. The unreflected light is absorbed, thus hitting the surface of the specimen. So the laser, so so you have a reflecting mirror, you have partial mirror, right? So through this partial mirror, that you have a laser beam coming out, right? So this is the partial transmitting mirror. So the laser beam. So some of it will be emitting out. So this is the laser beam that you see. So this is the laser beam that you see. So this is the materials. This is workpiece material. So this is the transmitting partial transmitting mirror. So the laser beam came out. So this is your workpiece material. So this laser beam will hit the surface of the material. Some of it will be conducted through the material. Some of it will be reflected through from the surface of the material. So the unreflected light is absorbed, thus hitting the surface of the specimen. So whatever reflected is reflected. Whatever not reflected will go through the materials, right? And if it's solid materials, mainly it's due through conduction. Right? On sufficient heat and workpiece start to melt. So if enough heat is being absorbed, then what happens is basically the workpiece will start to melt and evaporate. The physics of laser machining is very complex due to the scattering and reflections losses at the machining surface. So basically the physics behind it is very complex because of what? Because the energy will come from the light, right? So whatever being absorbed will be absorbed and used to heat up the material, but there'll be some that actually be reflected back, right? Uh, Heat diffusions into the bulk material cause phase changes, melting or vaporization depending on the power density and type of beam interactions. The mechanism progress from one heat absorptions and conductions to one of melting and then vaporization. So basically, so once enough heat is being absorbed with materials by the materials, basically, then the materials start to uh, turns into from solid into liquid, right? And if enough materials being absorbed, then the liquid will be vaporized, right? So 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 the laser lights absorbed by the materials, enough energy being absorbed, then phase transformations from solid to liquid will happen. As more and more energy being absorbed, then basically that liquid will turn into vapor. And when liquid turns into vapor, the material is being removed from the So machining by the laser occurs when the power density of the beam is greater than what's lost by conduction. So it says that machining happens when the power density of the beam is greater than is lost by conduction, convections, and radiations. And moreover, the radiation must penetrate and absorb by the materials. Right? So any questions? Okay, so power density. So power density is one of the elements that is important in laser machining. So you can calculate power density, which is the functions of the efficiency of the heat transfer to work surface. So this you can get it from the handbook. So different materials will have a different efficiency factor. Yeah. LP is laser power entering the surface. So this depends on the laser power of your system itself. And A is the surface area which energy is entering. So this is basically where the heat flux coming into the system, coming into the workpiece. So there'll be a area where the heat flux going through the materials. So this is the A, right? So this is examples of it. So basically, the so the 3000 will be your LP laser power. Your the 5 the circular area diameter is 5 mm, so the diameter is 5 mm, so you have to calculate the area. So this is basically uh, pi r square, and the efficiency of the transfer of workspace is 70%. So you just plug in number, you can get the answer, right? Okay. This shows the wavelength, the importance of the wavelength in laser beam machining. So if you look at this, so the light emitted from the laser is monochromic, one color and one wavelength, right? In contrast, ordinary light is combined of many colors and wavelengths. So laser materials will have one color and similar wavelength for that particular material. Right? So there's effect of wavelength on the absorption rate. So the shorter the laser wavelength, the more energetic photon can be absorbed by the greater number of bound electrons. So basically, the lower the wavelength, the easier for the energetic photon to be absorbed by the material. Therefore, absorptivity is increased